All right, so here we are, still Pkt5, class 18. We're going to be working on 2D quantum mom today, conservation of momentum. Well, tomorrow is blue day, so we'll be going over to the test 5A and then talk about which problems are blue and all that. And that'll be the official video key that everybody will watch. And that'll be tomorrow at 1:10 to 2 o'clock. So then today, we were going to play glance ball in the hallway today, but they're in the science building. They're coming in and putting all this tile work up on the walls. So up to about 6 feet, there's all this really nice looking tile. It covered up a lot of my paintings, which is too bad, but it's okay. So anyway, the floors are messed up. So we couldn't play glance ball. And if we can play it Thursday in the hallway, we will. And I'll show you a video of it. If not, then maybe Friday or I don't know, next week. I got to put the grouting down still. All right, so today, but we'll be on 2D conservation momentum, which brings in a lot of big concepts that'll help us in free body diagrams as well. And yeah, so we'll be on that today, Thursday, and then Friday we'll start to get into what we call duck walking and at least set it up. I went around today and gave stamps. I gave stamps for the 572 and 573. Now, I'm not going to have you guys submit that. Instead, you all will submit, you'll submit 5.8, what we're starting today. That's a more important worksheet. So you'll submit 5.8. And if the earliest you'd submit it would be this weekend sometime, maybe Sunday. So no rush on that, but you'll see the assignment. We met table 4 today. Yeah, I mean, I wouldn't mind meeting you guys too, but we'd have to make that unrecorded because I wouldn't want that to go out to the world, your personal information. So maybe we'll get that figured out next week. All right, so today's physics, we're dealing with the momentum suitcase vector again today. So the length of the arrow really just tells you the combination of mass and velocity. It doesn't tell you which, because they're both hidden in there. It does tell you the direction though. So this is what I went around and checked, and I would say of the students, the in-person students, 75% of them, I kid you not, 75% of them had it done or a good chunk of it done. So if you need to keep up with class, that's as far as we got yesterday. Now I'm not going to work on that today. That's homework. And there are 3 help videos on that. And they're in the comments below the screenshots from yesterday. And they're also on the worksheet. And they've been there for a month, because I'm trying to put those up ahead of time. So if you want to work ahead, you can. And there's the key to it. This is, I think a student made this a couple of years ago, did a better job than me. So I put her key, and I'll put this in the screenshots, and I'll also put it in guide 2 of the Facebook group. So that's what you should have on your paper right now for 5.7. Okay, you know, it's weird. It's I mean, think about it. We did that one together. That was the most probably straightforward of all of them. This one, the number 2, that blue, the first, okay, this first part, this is the first blue vector that comes in. That's the first momentum vector. Part B, I mean, the object B wasn't moving to begin with. And it's a glancing blow. They aren't the same mass. So B took off that way, and then you're supposed to figure, and it told you that. And you're supposed to figure out which way did A end up going. The only way to do that is, if you're doing construction, is to do head to tail. And we got that's for your answer. So 1 arrow turns into 2 arrows, but that shouldn't be so weird. When you're playing pool, 1 white ball with an arrow coming down, its mass times its velocity, hits 15 pool balls, and all of a sudden one arrow turns into 16 arrows, assuming all the balls move. And then this one, in this case, I play pool. So if I haven't played in a while, but I used to always play every Friday. Me and some buddies would always go play pool. And if you're a pool player, you already are familiar with what we're going to do today, with the physics we're doing today. Your brain is. I mean, mathematically, maybe not, but your brain is. So pool ball comes down, hits all the other balls, and so one vector turns into 16 vectors, and it's all conserved. That's the weird thing about it. It's all conserved. When I was playing pool at a place called Winchester's, which maybe your parents remember, first time I was a sophomore in college, I guess. And so I got playing a guy, and the guy knocks in the 8 ball on the strike, on the break. And I'm thinking, all right, I won. So then the guy got into a fight because the guy said, no, man, I didn't know that. When you knock the 8 ball in on the break, you win. That was good. He did it 2 or 3 times. Not to me, once to me. And anyway, college story. So on this one, I make my ghost green. This person didn't. But for this, the hardest one on the sheet, here you're given 3 arrows, and you got to come up with the 4th arrow. It's just always mathematically, it's just bizarre to me, but this works. So you're given this initial arrow of B, object B. It tells you what object's A initial arrow is. That's a mass times velocity and the angle. And then it looks like A comes in, it gets hit by B, and it takes off conservation. It doesn't lose its mass. So it goes from 400 kilogram meter per second to 800 kilogram meter per second. So since the mass didn't change, A must have come in, got hit by B, doubled its speed, and then went off in that direction. Okay, like maybe billiards. Okay, one ball comes in, gets hit by another ball, doubles its speed, and goes off in this direction. But then B had to it was going at 750 kilogram meter per second. It ends up at 130 kilogram meter per second. So since the mass didn't change, the velocity must have dropped off by what, 6 times, 5 times? Okay, so if it was going 5 times slower after, after it hit and knocked the bejeebers out of ball A, it really slowly rolled backwards. Okay, so it's telling a story with vectors. Anyway, that's your homework. Now let's go to today's topic. The homework for today is the easiest one on the sheet. Homework. And for them, it's for 2 dynos. Oh, but for you, to keep up with the pace of the class, you want to do that tonight. I don't have a help video on it. I do on some of these, but not on number 1. We're going to spend the rest of the time. It's going to take us all the way till 2 o'clock, and maybe we'll finish number 2. Now, this will get us into some historical stuff. It'll get us into more than just the problem. But so you want some notes, take a few notes out. Remember, you're going to get 75 points worth of notes. So that you'll be turning in on April the 8th. All right, so here we have 2 hover discs. And in class, there's these little bouncers. They're discs, and they're rubber around the outside. So they hit and bounce off each other in a supposedly elastic collision. They're hover discs, so they don't deal with friction. And this is what we do in the hallway. This is glance ball. So one's coming down from the north end of the hall to the south end of the hall, and it hits disc B, which starts off not moving, okay? So I'm gonna give you a minute to first just reading number 2, and then maybe lightly in pencil, try and sketch out what you can on the drawing over here, okay? So let me give you a minute to do that. I'll put it on pause. Okay, so we have the momentum of disk A coming in. And remember, that's mass times velocity. Now you get to write small or put it on a piece of paper and then, you know, put a note, say see paper, and include your paper on the packet. Maybe that's a good idea, because there's quite a bit of stuff that goes with this one. Equals MA VA naught. A student asked, why do you use I sometimes and not other times? Not is kinematics historically, meaning initial, and then when Newton switched over to doing momentum, he started saying I as initial. So some textbooks give you VI, some textbooks give you V naught. I think old school engineers will still use naught, and I'm kind of old school, so I use naught for kinematics and I use I for other things. Doesn't matter. Okay, so that's what we have, and then we know that it comes off. Okay, so it's going to veer. A veers to the right. Hold on. Immediately upon collision. This is where you could get a little confusion. A glances off, and it should say and veers to the right at an angle of 30 degrees. Well, that's from A's perspective. So if I'm following A is going south, and to the right would be to the west. So looking at it from a map view, to the right appears to be to the left, but not from A's point of view. That's weird, I know. So 90, and then it goes 30 degrees, veering. Veer, when you say veer, like if I'm playing basketball or something and I come up to the top of the key and I veer left, that means I was running straight for the basket and then I veered left. Veering usually means between 0 and 30 degrees. A slight adjustment, slight change is a veer. So I don't know how long to make it, but I know that the line of action looks like this, somewhere along that line. So there's lines of action. We're not doing head to tail here, but still line of action is important. So that's the LOA for the aftermath. The collision is right there, then A goes off. Okay, and then from there, we're supposed to find out what is A's momentum. Okay, we know we know it has a mass, but what's A's momentum? What's B's momentum after collision? There's a lot of things to know here. How are we don't seem to have enough information. Okay, so let me give you a shortcut, very dangerous. And I know it's dangerous, and I'm telling you, on the last test, which I've got about 5 more to grade, 5A, but a lot of you were using the range equation shortcut when you shouldn't have. Range equation's very tempting to use it all the time. And some of you just use it all the time. Remember I said when we went over that, we derived it. I said, be very careful, skull and crossbones. This is very dangerous because people use it in the wrong situation. This is only good for type 2A projectile motion when it takes off and lands at the same elevation. But many of you used it on type 2B. Also, many of you use type 1 equations when you're trying to solve for type 2B equations. That's why you had a flow chart. Anyway, that happened both for you guys and for in-person students. More than it's ever happened before. And I know I'm warning you, but it's just communication breakdown with this stuff. Anyway, so I'm giving you another shortcut with danger. So emphasize the danger. But we have to use it or we can't solve this problem. So here's a dangerous shortcut. Okay, a couple of ifs. If the masses are the same. So if in a collision, if MA equals MB, two masses are the same. And if, another big if, this is one students forget, if one of them, let's call it mass B, initially is static. Initially is static, meaning not moving. Then, if those two conditions are met, then the angles of motion after collision are complementary, not congruent. They're complementary. What's that mean? Wait. Okay. What's that mean? Complementary?
They add up to equal 90 degrees.
Thank you. There's your zoom point. So add up, in other words, angle A plus angle B equals 90 degrees. It's one of those ACT, SAT. By the way, I sent you all for our company, Ask Me Tutoring, I sent you all an invitation to our SAT. I got Jamie Rensel for math. She's excellent. Kara Stoltenberg, up and coming English, excellent instructors to prepare you for the SAT. Those kind of things like complementary, supplementary, you know, all that geometry stuff you've forgotten. We go, and Jamie go over all that, kind of give you a primer, get you back up to speed. So when you take the SAT, if you're a junior, and I also send them out to seniors too, just for grins, and for sophomores, because a lot of sophomores want to start getting ready. So a little plug there. And that's coming up April 7th and 8th in the evening, just by, normally we're live, but now we're doing it by Zoom. So there's your dangerous shortcut. We're going to use that now to help us solve this problem. So it does meet the criteria. The two masses are the same. And one starts off static. This is, if you're a pool player, this is how you play pool. You know this in your brain. If you ever play pool and you're any good at it, if I got the 3-ball and I'm trying to put it in the corner pocket, my brain's thinking this. This is how I got to hit the white ball's got to hit it, so that the combined angle after collision, it also tells you where the white ball is going to go for your next shot, but the combined angle will add up to 90 of the white ball and the 3-ball, their movement. So now I'm going to go ahead and set this up. Let's see if that's right there. Okay, so this will be like this. I'm going to make that purple. I'm going to make object B purple. It's going to head off at this direction. That's its line of action. Come on, man. Somewhere along that line will be the vector. There. Okay, so I know that. So that tells me that, so far so good. You guys can stop me. I get the chat open, or you can. So I'm trying to figure out what those two arrows are after collision. So, I don't have my arrows, wooden arrows here to show you, but in class we do this demonstration with arrows. But I have an arrow pointed down, and so all of a sudden that arrow gives birth to two other arrows. Not spontaneously, because they actually hit another one, but mathematically it seems strange. I'm going to make this long. I'll go ahead and make an arrow on the blue on object A. Let's say it's that. So that would be PA final. Now I know what you're thinking. How did he know to do that? Well, I knew what, how did he know how long to make that length? Now hold on, I'm doing this. I can change it, I can adjust it. That's my first guess. All right. Now, here's what students do that make mistakes on tests. They're going to get good partial credit, but here's what they do. Okay. There we go. They do this. They're trying to figure, this is going to make two right triangles. Remember, I never told you this, but a vector at an angle is the hypotenuse of a right triangle. So the two right triangles that would form, this is a mistake. This is wrong. But this is what students do on the test all the time. This breaks a fundamental law of physics. Anybody know what law, or it is a broken law of conservation of momentum, but why? How did I break it? Anybody want to hazard a guess? Why is this an impossible situation?
Is the total amount of like energy at the end lower or higher than it is at the start?
It would be, and I agree with you there. That's obviously a violation of the first law of thermodynamics. You can't have more energy out of a situation in either direction. It's a little bit nebulous there because energy is a scalar, so energy doesn't have a direction. So although I agree with you, there's a more direct answer. It violates the law of conservation of momentum, but look. Okay, so let's go back. We need to revise our conservation. We need to beef it up a little bit. So conservation of momentum, we've said, is summation of pi, little pi, is equal to the summation of little pf. Well, okay, but now we got to make it two-dimensional. So it's summation of little pi in the x direction is the same as the summation of little pf in the x direction, and little pi in the y direction must be the same as the summation of little pf in the y direction. So I just doubled all my equations for two-dimensional. Now, if we were to go three-dimensional, which I promise you I will not do that to you, I don't even know if college does that to you, but if you go 3 dimensions, then you go summation of pi in the z equals summation of pf in the z. So you have to break this up into its components. So now let's establish which way is x and y, and I should have done that from the very beginning, but let me go back and do that. So you need to set up a axis here and establish for the reader what you're calling x and what you're calling y, and what's calling positive, what's negative. So I should have done that right off the bat. So this is, let's make the direction of motion x. That's a common thing to do. And so we're going to call this positive x. I'm going to say to the south, like we did on day 1 of school, or day 2, where I said to the south is positive. It can happen. It's how you set up the axis. Otherwise I'm saying the object's moving in the negative direction. I've got to put negative signs. I try and avoid negatives and decimals as much as I can. And let's make this positive y. Okay, so to the south is positive x, to the east is positive y. So that means, so what I violated here is I violated this. Because initially, how much momentum is in the y direction? Initially, how much momentum is moving east and west before collision?
0.
None, right? 0. So I can't have any momentum at the end in the east-west line. I had a student a few years ago say, wait a minute, are you telling me that you just manufactured motion east-west out of whole cloth? You just boom, and said, there's motion now east-west. Yes, it's legal to do that in physics. This is true, this is the overriding law of physics. You can do something as long as you kill it at the same time you do it. So I can have motion east-west like this PAF. I'm gonna run into trouble, I just realized. I'm gonna make it a little bigger. Oh, shoot, okay. Just ignore me for a second. I'm gonna make that just so you can see it better. And that was still wrong, but I'll go ahead and continue. Okay, that'll line up better. Uh-oh. You can do things in physics as long as you kill what you just did. You get away with it. Like time can go backwards as long as you kill it with something going forwards. And this happens all the time. Positrons may go backwards, electrons go forwards, as long as they annihilate each other. If they both come out of a neutron or something, as long as you and one annihilates the other, you can do it. So you do have, like we think of time as a river flowing and it flows in one direction, but there's little eddy currents in there where time can go back as long as it doesn't take very long and as long as it gets killed. As long as there's something moving forward that kills it. Matter, antimatter, right? You can you can make matter as long as you make antimatter. And here I can manufacture momentum east-west as long as I kill it. Let's say momentum moving west as long as I kill it with momentum moving east. But what this does is it never kills. This doesn't do it because this gives me momentum. It gives me more momentum moving east, the purple, than it does west. And that can't happen. So I've got to erase this part of it and redraw that leg of the triangle. So I get this blue triangle. Let me go ahead and finish that out. Blue triangle. Colors are huge. Just make that up. No, hold on. I'm trying to make this look pretty because this is for the official record here. Okay, whoops. Hoping to have kids in Bangladesh watch this stuff. I'm trying to learn a little physics. I don't want to make it look bad for them. So we have, now I'm gonna make this a blue right triangle because every vector at an angle is the hypotenuse of a right triangle. So I have a blue right triangle and I'm gonna have a purple right triangle. Blue comes along this way. There's the X leg, the north-south X leg. Here's the here is the east-west, the moving west Y leg. So the leg, the east-west leg of the purple has to be the same length as the east-west of the blue because I got to end up no harm done. I can't have any momentum ultimately in the east-west direction. That's 1, 2, 3, 4. And you do your own thing, which the ruler or something. 1, 2, 3. Okay. So this is now my purple. And so I have a purple triangle. Here's the vector. And now I'm starting to get a feel for what the result collision will look like. Now we're thinking like Newton. And that's purple. Newton figured this stuff out around 1690s, which we still use today. Imagine you develop a law and then they're still using it in 2300, 2320. So this is P PBF. There was no PB naught because it was zero velocity. And now I can feel pretty safe, but every class there's been a student ask a question at this point. One student tends to raise her hand right now. Anybody want to ask what the question? Oh, hold on. Let's go ahead and make that. Let's show these congruent here. That's important. Show the congruence. All right. So, and then we'll do this too. Let's put all the information here. This was 30 degrees. And this was 60 degrees because they're complementary. Okay. But there's one thing I haven't really talked about that might cause you concern. Anybody see it? I tried to draw it about right. Nobody has a question? Okay, in every hour somebody's asked, they said, wait a minute, I get that the east-west has to cancel, but how did you know how long to make it in the first place? Why didn't you make PAF, you know, this long? Why not make it way down there? Just make that PAF. How'd you know to make it that long? What say you? What limited me on how long to make PAF? What's the limiting factor? I see the limiting factor in the east-west, but what's the limiting factor in north-south? For the blue and the purple triangle, what dictates their length, their combined length, north-south? Sophia's trying to answer. Oh, there it is. Go ahead.
The force you start out with, like
Right.
how fast the first object is moving?
Right, and I don't want to say force, but I hear what you're saying. It does have a force, but we're not there yet. We're at momentum. And so you're right. It's the combination of the mass times velocity to begin with. You cannot violate conservation of momentum either way. I can't violate in the X as well. So this leg, the blue leg of this right triangle, and the purple leg, when I add those two up, I have to get that length right there. I don't know. I kind of tried to eyeball it in. And if I got a ruler, that seems about right. So on your picture, just kind of make it so it seems about right. We're not, like I say, we're not constructing. We might do that later. We're not doing head to tail on this. All right. So, so that's sort of the anchor that dictates what those two right triangles look like. Okay, very good so far. But now we got to give numbers to everything. We know that this is we know this is MA VA final. We know that is MB VB final. But now we got to know what all those variables are. But hold on a minute. Hold on a minute. We catch another break here. Didn't we say that all the masses are the same in this case? Otherwise, I couldn't have used a shortcut. So you know what I can do? I can just erase on the subscripts on the masses. Those are just M's. Those are just M's. Really no need to say MA or MB. Sure. So let's just get rid of that MA, MB. We can't say that about velocity. Okay, so this brings up a little history. So we talked about this in class too. So Descartes, Rene Descartes, if you, I don't know if you've studied any philosophy, but Rene Descartes was a Frenchman, 1650s. He was kind of between Galileo and Newton. He was alive when Newton was alive, and I think he was towards the end of Galileo's death. He was sort of in there. He's a French guy. So brilliant, great philosopher. But he looked around him and he sees all this movement, birds flying up and you know, carts going by and horses. And so he says, you know, there's all this motion on Earth and I guess in the universe. He said, but everything gets hit and bounces off each other. He said, if you rewind the tape and keep rewinding it and rewinding it, like if I see two objects going this way, at some point they're going to come back and they were together at one point, right? Something hit them to make them move. Or if I want to reverse a pool game, I can get back to the original break. And so he said, you could do that with all motion. And you can, if you keep going back and back and back, there's something, some entity, of course, people, you know, humans tend to personify things. So he said, there's some entity that was what he called the prime mover. And if you look up prime mover, so it's a philosophical statement that something had to get the ball rolling, right? Something had to get it moving. And that's what he called the prime mover. Now, modern day physicists would call that the Big Bang. But reversing everything back, we eventually get back to this infinitely small, you know, singularity. And that's where then the Big Bang came. Speaking of the Big Bang, so when the Big Bang occurred, I was talking about when you can have something as long as you take it away, right? When you create matter, you create antimatter. Well, in the Big Bang, the idea was that all this matter and antimatter was created, but what every bit of material in the universe is that little bit of leftovers of mass, things that have mass that did not get annihilated in the Big Bang. Most everything got annihilated, 99.999%. And we're that little tiny bit, all the mass in the universe that did not get annihilated. Anyway, so there's the idea of you have one. And then, so then the question is, well, why? What law of something got violated? Okay, so that's like modern day state of the art questions that are still going on. But so what Descartes said was, there is like this conservation of this motion, conservation of motion. He didn't say that exactly, but he's saying conservation of velocity, essentially. Well, Newton argued with him and said, no, wait a minute. No, they did do some letters back and forth. He said, well, you're kind of half right. It's not, you cannot discount inertia. You can't discount this resistance to movement. He said, but you are correct in that there is conservation, and there is a prime mover, but it's conservation of momentum. If you bring in mass and velocity, that is conserved, and that is a law we still use. Newton said, if you take a huge net and put it around the entire universe, and back then they didn't know there was anything beyond the galaxy, right? They thought they were like points of light up there. They had no understanding of the universe really back then. But he said, if you put a big net around all of that's known in the universe, in the known universe, then every bit of momentum will be conserved. If something's hitting something else, that gets conserved. Something going to the left, it gets conserved, and something going to the right. And that is true. That's a fundamental law of physics, is this conservation of momentum, not conservation of velocity. Okay. Just want to point that out because that's going to play a role here in a minute. We're about out of time, but let's see how far we can get here. So far, everybody okay with this? It's taken me 40 minutes to get through half a problem. Physics, if you haven't noticed, just kicked up a notch in difficulty. We still got to know. Okay, so now let's set the equations up. So we're going to break this up into x's and y's. So let's start off with the x direction. So in the x direction, we have summation of pi x equals summation of p final x. So initially in the x direction, I have m times va naught. And that's all I have. I could say plus 0, I guess, because b is not giving you anything initially. And then at the end in the x, I have, Okay, here we go. I'm going to need this leg, and this leg of the blue triangle will be, I tried to avoid it as long as I could. This will be MVA final cosine 30 degrees. Okay. And this, yeah, so, and this will be the purple. This will be no, the M's are the same. VB final cosine 60 degrees. So those two have to add up. Starting to get nasty. This ain't the bad one. Number 3 is the bad one. Okay, so then let's go ahead and finish this then. Then that is MVA final cosine, add those two up, those two legs, cosine 30 plus MVB final cosine 60. Okay. Now, what can I do with my M's? What can I do with the M's here? M.
Divide?
Well, bring out the green kill pen. M is common to everything. So M can be killed. I can just divide both sides, like you say, divide both sides by M. Goes away, goes away, goes away, goes away. So we end up with probably my final equation for today. VA naught equals VA final. I could write a number in for cosine 30, but I'll just leave it as cosine 30. I know cosine 60 is 1/2, but I'll leave it as cosine 60 plus VB final cosine 60. Boom. And there's an equation. I still have too many unknowns, but now I got something I can work with. All right, that's the X. If you want to play with it tonight, you can do the Y, but let's save that. We're getting down. We're already ahead of the in-class kids. I don't want to get too far ahead. So we'll save the rest for not tomorrow, because tomorrow's Blue Day. We'll save the rest for Thursday, and then we'll start to tackle 3. The back is like head to tail, and you're going, oh, please bring me back. Once you're done with number 3, you're going to be begging for head to tail. All right, any questions on what we just did? Tonight, your homework is number 1, which is a little more civilized. It's still collisions, and you still got to figure out, you got to do it this way using conservational minimum, but I want you to at least try it. There is no help video, but I want you to try it, then we'll talk about it. Okay, so I'm going to go ahead and let you guys go unless you want to talk or have a question. Any questions? Too bad.